Periodic trends are trends across the periodic table that determine the chemical properties of elements in relation to the other elements around them. Periodic trends are a significant part of predicting chemical reactions. Determining KSV values, predicting polarity in molecules, and doping semiconductors. Are a few of the important ways chemists use periodic trends. In order to explain periodic trends, the mechanisms behind how they work must be explained. Coulomb's law is an important mechanism in explaining periodic trends. First published by Charles Augustin de Coulomb, Coulomb's law determines the electric force between two charged particles. It's given by the equation F equals K Q sub 1 Q sub 2 over R squared, where F is the electric force in newtons, K is the Coulomb's constant, Q1 and Q2 are the charges of the particles in coulombs, and R is the distance between the particles in meters. In chemistry, we aren't concerned with the value of the electric force, rather, we're concerned with how the force between the nucleus and the electrons of atoms relate between the same force in other atoms. So, as the charge of the nucleus increases, the force between the nucleus and the electrons also increase. Likewise, as the distance between the nucleus and the electrons decreases, the force also increases. This is why core electrons, which are closest to the nucleus and don't participate in chemical reactions, as the nucleus holds onto them with a strong electric force. Likewise, valence electrons determine the chemical properties of elements, as the nucleus does not hold onto them as strongly as core electrons.
Effective nuclear charge is essentially the force holding an atom together due to the net positive charge experienced by non-valence electrons. With this being said, we can conclude that the effective nuclear charge increases going across a period. This is because although there are more electrons on the atoms as you go across a period, those electrons are added to only the valence electron level, not the non-valence electron levels, which are responsible for the effective nuclear charge. And since the number of non-valence electrons stay the same and the number of protons increases going across a period, the effective nuclear charge also increases going across a period. To show this, let's take a look at lithium, beryllium, and boron, three of the elements in period 2. Now, as you can see here, as you go across the group, the number of non-valence electrons is 2 for all three of the atoms. However, the number of protons increases going from lithium to beryllium. Therefore, we could say that boron has a greater effective nuclear charge than beryllium, which has a greater effective nuclear charge than lithium. And this concept of effective nuclear charge could also be used to explain certain periodic trends, as you will see later. Electron affinity is a measure of the energy released when an electron is added to a neutral form of an atom. This means that a more negative change in energy would correspond with a higher electron affinity value. With this being said, the general periodic trend for electron affinity is that it increases going across a period and decreases going down a group. The increase in electron affinity going across a period can be explained using concepts of effective nuclear charge. Going across a period, an atom experiences greater effective nuclear charge. As a result, electrons are more attracted to the atom as you go across a period. Since there is a greater attraction, more energy is released as you go across this period. As for going down a group, electron affinity generally decreases. This is due to the increased shielding effect of electrons as you go down the same group, since more energy levels get added going down a group. This increase in shielding blocks the incoming electron attraction to the nuclear charges and therefore results in a decrease in electron affinity. Ionization energy is the exact opposite of electron affinity. It is the energy needed to remove an outermost electron from an atom in its ground state. With this being said, ionization energy generally increases going across a period since the outermost electrons will be closer to the nucleus and are therefore more attracted to the nucleus. The ionization energy would decrease going down a group since the shielding effect increases as you go down a group. As a result, the outermost electrons are less attracted to the nucleus and require less energy to strip away.
Shielding is one of the mechanisms that influences periodic trends. As you go down the periodic table, new principal energy levels are added. As every new principal energy level is added, a new layer of electrons is being added. Shielding involves inner core electrons, preventing the outer electrons from feeling the full force of the nucleus. The electrons also subsequently get farther away from the nucleus. This decreases the nucleus's pull on the electrons, which makes it easier to remove the outer or valence electrons. Therefore, as you go down a group, properties like ionization energy or the energy required to remove electrons decreases, while the size of the atom increases.
Electronegativity is another periodic trend that chemists find useful. Electronegativity, symbolized by Greek letter chi, describes how strongly atoms like to hold on to their electrons when forming compounds. It also predicts where electrons will spend most of their time in a molecule. It can therefore predict polarity. Electronegativity increases from left to right on the periodic table and from bottom to top. This makes fluorine the most electronegative element on the periodic table. This is because fluorine is the smallest element, thanks to Zepf and Coulomb's law. Electronegativity increases as atoms get smaller, and shielding causes electronegativity to decrease down a group. Let's take water for example. Oxygen has a much higher electronegativity than hydrogen, so electrons spend more time near oxygen than near hydrogen, making oxygen slightly negative and the hydrogens slightly positive. This makes water a polar molecule. Another example is the compound cesium fluoride. Cesium is the least electronegative element, while fluorine is the most electronegative element. This makes CSF the most polar ionic bond of any molecule known.
Atomic size is an important periodic trend. As you go across the periodic table, the Z effective of the elements increases. Therefore, the atoms further to the right of the periodic table will pull their electrons in closer than the atoms on the left side, which results in a smaller size. As you go down a group, shielding increases, preventing the nucleus from pulling in the electrons closely. Also, new principal energy levels are added. These factors increase the size of elements as you go down a group. From this, we see that cesium is the largest atom and fluorine is the smallest.